Here I am telling you about why low flow. The primary reason is efficacy of the volatile anesthetic increases. It saves a lot of volatile anesthetic and thereby decreasing the cost. Sometimes you can save almost up to 90% of the inhalation anesthetic agent. What do you do using your open circuits or paying circuits? So you are using very, very high flow. What essentially you are doing is you are throwing your hard-earned money down into the drains, literally. You want to know how? I will explain to you in a short. Imagine Asian consumption per hour for sevoflurane is given by this formula 3.3 multiplied by fresh gas flow multiplied by the dial settings. So imagine an anesthesiologist who keeps 3 liters of flow and a dial is on 3. So in an hour he uses 29.7, nearly 30 ml of sevoflurane. So if the case is going to last for 5 hours, you are going to end up using 150 ml of sevoflurane. There's another anesthetist who uses 1 liter of flow. So he or she keeps the flow at around, the dial is at around 4. So he or she uses 13.2 ml per hour. So in a 5 hours case, it will end up using 65 ml of sevoflurane. There's another anesthetist who uses 0.5 minimal flow. So the dial is on 5, so it's about 8.25 ml. So in 5 hours, it will be 40 ml. And there is another anesthetist who uses only metabolic flow of 0.2. So the dial is on 6. So he ends up using 4 ml per hour. So in 5 hours, he uses 20 ml of sevoflurane. One anesthetist uses 150 ml of sevoflurane. Another anesthetist uses only 20 ml. Look at the savings. Each ml of sevoflurane, at least in India, is about 40 rupees. Imagine your sevoflurane bills will be around 6,000 rupees for the first anesthetist and will be hardly 800 rupees for the next anesthetist. So that is the kind of savings which we can do. There's another reason why low flow. It is more physiological. Whenever you give low flow anesthesia, say 0.5 liters or 200 ml per minute, it leads to major improvement. It causes gases to get warm. They also get moist. And that's the most beautiful function of the nose. So whenever we are passing a supraglottic airway device or an endotracheal, we are bypassing the function of the nose. So the dry and air that enters inside, it damages the mucociliary action of the respiratory tract epithelium. So post-operative pulmonary complications can always be more if the mucosa is going to be dry. Instead, if you have a technique by which you can give a lot of humidified air to the patient or humidified gases which are warm, there is always better homeostasis of temperature, less hypothermia, and the moist as well as heated air will preserve the function of respiratory epithelium and it will not cause post-op pulmonary complications. So it's more physiological to give low flow anesthesia. This has been explained years ago in multiple papers that our modern anesthesia machine, when we reduce the flows to such levels of 0.3 or 0.5 liter per minute, you can safely give anesthesia with sevoflurane or desflurane. It's a perfectly safe technique. It leads to a lot of cost saving and improves temperature homeostasis. Now, some of you will wonder from where this heat is getting generated, from where this water is coming, how it is becoming moist and warm. To give you a very simple explanation, we use soda limes. So soda lime lumens itself carbon dioxide, which reacts with water in the soda lime, thereby giving rise to carbonic acid. This carbonic acid reacts with sodium hydroxide, thereby causing sodium carbonate, water, and heat. So this is where the water and the heat, which I was mentioning about, which gives rise to moist and mineral gases. The next step is of course sodium carbonate reacts with calcium hydroxide, thereby giving rise to calcium carbonate and sodium hydroxide. Once all this sodium hydroxide is gone, then the soda lime starts getting acidified and then the indicator changes. And that is the time we change our soda limes when it turns into wine. So this is how the absorption chemistry takes care. Now we come to the most important part I was telling you about. It reduces the waste and it reduces the pollution. I mean, today's times when we have COVID virus, that's what I was telling you. Everybody's talking about the incubations, the incubation boxes. People are talking about uh, positive pressure OTs, the negative pressure OTs, the changes occurring every of the air into the laminar flows, so on and so forth. Everything has been discussed, but hardly anybody is talking about reducing the flows. In 40 years ago, this virtue demonstrated that when you reduce the fresh gas flows from say 2.5 liters to about 200 ml per minute, concentration of nitrous oxide at the patient's head end was about 9 times lower. Keep your flows as low as you can so that the viral load, even if the patient is positive, will be so low in the OT pollution. I'm not worried about intubation that much, but I'm very much worried about the extubation part of it. Because that is the time the patient is coming out of anesthesia, or he or she may cough or sneeze or do all sorts of things, vomiting, all sorts of things may give rise to a lot of aerosol generation. So that is more important. But intraoperatively, also, if you keep the flows low, you will cause less pollution. Lastly, it's not about only the theater pollution we are worried about, but the entire pollution of the planet Earth, the mother, that is the greenhouse effect. A lot of infrared radiation comes down to the planet Earth. Some of it gets bounced back from the atmosphere, and some of it reaches that Earth and thereby giving rise to warmth to us. Now, when we use these nitrous oxides, isofluid, CO fluid, S fluid, and halogen, all these halogenated compounds basically are greenhouse gases. So what are these greenhouse gases? See, greenhouse gases are the ones who will absorb this radiation and will scatter the radiation in all sorts of ways. So now, another problem with these agents is they have ozone depleting properties. So they do two things. One, they deplete the ozone that is there in the atmosphere, thereby creating black holes through which the sunlight can directly hit the earth, thereby causing global warming. That's one. And the second thing what it does is it absorbs this radiation, which is getting reflected or bounced back from the surface of the earth. It will absorb and it will scatter in all the directions, thereby further causing. So now how much is the percent? Now, thankfully, anesthesia contributes only 1% to this. The major industries are the fertilizer industries, the cars, the automobiles, the aviation, and the refrigeration industry. As seen in this chart, CFC compounds are the most dangerous ones. You can see the global warming potential on the right side, which is thousands of years, as compared to nitrous oxide, which is 298, haloisoCO tests are about 280, 315, 575. Let's come to the definition of a low flow. So when do we say that we are using low? So low flow anesthesia is an inhalation technique in which a circle system with absorbent is used with a fresh gas flowing flow that is less than patient's alveolar unit volume. Usually it is taken as 1 liter per minute. Now there is a classification, Baker's classification, where it gives various figures like metabolic flows said to be 250 ml per minute, 250 to 500 is minimal flow, 500 to 1000 is low flow, and so on and so forth, where you get more than 4 liters considered as open. There is another way in which you can define this low flow anesthesia, and that is by the percentage of the rebreathing that takes place. Now, on this chart, on the X axis, you will have fresh gas flow, and the other axis you have 0 to 80. Now, look at the 6-liter mark. At 6 liters, is hardly any fresh rebreathing happening. It's about 5%. At 4 liters, is about 15–18% of rebreathing. At 2 liters, it's about 35% of rebreathing. At 1%, at 1 liter, it's about 55% of rebreathing. And less than 1, it's about 75%. So somebody can always redefine it that whenever an inhalation technique is used, where there is more than 50% of gases are rebreathing taking place, that is also a technique of fresh gas flow, low force. Okay, so that is another way you can define this particular. Now let's come to the concept of time constant. This is a concept which is very important to understand how we induce a particular patient on inhalation anesthetic agent, as well as whenever we make any changes in the dial, how much time it will take to reflect into the patient's system and ultimately the lungs as well as in the brain. So time constant is a measure for the time required for changes in the composition of fresh gas to lead to corresponding changes in the composition of the gas in the anesthetic system. And it's given by the formula T, time constant, is equal to Vs, that is the volume of the system, divided by Vd minus Vu, that is your inhalation anesthetic delivered minus the inhalation anesthetic uptake. Imagine at the end of first time constant, the concentration of anesthetic agent gas in the system, by complex calculation, they have found out it's about 60%. The second time constant leads to 86.5%. The third time constant leads to 95%, and the fourth time constant it almost takes to 9. So it usually takes about 3 to 4 time constant to reflect the exact change which you wanted or which you intended when you moved that dial. Knowing this, let's calculate what really happens when you do a particular case in a 70 kilo adult patient. At assumed volumes of 5 liters for a system, the one which you are using your machine, and 2.5 liters for the lung capacity, the vital capacity, and an uptake of about 0.35 liter per minute, you will get following time. Fresh gas flow at 8 liters, you will get about 58.8, say about 1 minute as time constant. At 0.5 liters, it becomes 50 minutes. So your patient is going to take more time to go under if you're using very low flows. If you're using very high flow, then the patient obviously will go under much faster. The principle behind that is the time constant. Why does it happen? Obviously, you will see why it is happening is because when you change the control dial, the fresh gas flow gets splitted into the two things. One is because there is a splitting valve. One will go as a bypass and the other will go into the vaporizer, pick up the vapor and will come into the other. So if you increase the fresh gas flow, automatically, even though it's a splitting valve, more air will go inside the vaporizer, will pick up more agent and will get delivered. This is a very simple principle. So what is the monitoring for safe performance of low? What is essential? One thing is sure, I'll always say this, if you don't have this infrastructure in your operation theater or in your anesthesia machine, please don't do low flow anesthesia. So always you have to be safe. If you don't have adequate infrastructure, please don't do low flow anesthesia. And what do I mean by infrastructure? You must have a good anesthesia machine, not only capable of doing its own leak test, or it should have a compliance compensatory mechanism. but you should always have a respiratory gas monitor, and certain parameters always include that, like inspiratory oxygen concentration, expiratory oxygen concentration, inspiratory gas. You're using nitrous, inspiratory nitrous, or expiratory nitrous, airway pressures, the flow volumes, the loops, the anesthetic concentration going in, coming out, and expiratory CO2, inspiratory CO2, compliance, whatever the pressures, all the parameters are absolutely mandatory. You cannot do a case if you don't have this kind of infrastructure incorporated in the software of your machine, or you should have monitors.